Okay, so we are in lecture 14 now. So in lecture 13, we have introduced the Boltzmann transport equation. Boltzmann transport equation just state that our electron's motion in phase space. Okay, so phase space contains two informations like position of our electron gas and momentum of our electron gas. So in order to represent its distribution, we introduce electron distribution function f, and this f is reduced to Fermi-Dirac distribution when we consider equilibrium system. However, Boltzmann equation describes the motion of our electrons under the non-equilibrium case. So by solving the Boltzmann equation, we can get the electron distribution function at non-equilibrium case. Okay. So at the end of our previous lecture, we have talked about the one-dimensional structure, one-dimensional system, and we have found that if we consider and B, if we consider an infinitesimal volume in the phase space at t equal to 0, and if we just allow a short time transient, for example just 1 picosecond, then the electrons originally or initially placed in this area are mapped into a different box inside the phase space. Okay, so if we have 1000 electrons originally, then after a short time later there will be also 1000 electrons in this box. Okay, if we ask ourselves, then at 1 picosecond, how many electrons are there? How many at t equal to 1 picosecond? If we ask this question to ourselves, this is nothing related with the 1000 electrons at t equal 0. The 1000 electrons originally located or occupying this box now all moved to this position. So maybe somewhere here there was, for example, 100 electrons, then after 1 picosecond has elapsed, then they will move to this box and we will have, for example, 100 electrons. So I mean that this is just motion of our distribution function inside the phase space. So whenever time elapses, our group of electrons moves and their motion just follows Newtonian motion. So this is the one we have discussed at the end of our previous lecture. However, if we introduce scattering, then this journey is disturbed. For example, let's say this position. So due to the Newtonian mechanics, it should move in this way. This is the given and predicted behavior of our electron originally located at this position. Here position means that real space position and velocity. However, during its journey, let's say that at certain time instance, for example 0.3 picosecond, something happens. What is that something? Something means that scattering event happens. So let's say that its velocity just drastically changes by the scattering event. So start from t equals 0 and time elapses and it moves. However, at t equal to 0.3 picosecond, suddenly something happens and instantaneously it is just jumps into this new position inside the phase space. After that, what will happen? So after that, it will also just move in usual Newtonian motion. So behavior of our electrons inside this phase space can be regarded as just having two phases. One phase is just a normal motion according to the Newtonian motion, and another phase is some instantaneous interaction between our electron and environment, and that is described by the scattering event. And in the phase space, it is described as just a jump or just a sudden disappearance and appearance at certain positions. Up to now, I have discussed about the description of motion or change of distribution function in the phase space. So now let's go to our main discussion today. So you know that this is quite reasonable to describe our dynamics in this phase space. However, unfortunately, description in phase space introduce increase in the dimensionality. So simply speaking, phase space has more information, additional information about the phase space. Instead of having the number of electrons at a certain position, number of electrons, that is the thing we wanted to have usually. However, this distribution function have another additional information. At a given position, how many electrons are there, and what is the velocity distribution of this electron gas. That is additionally given by this distribution function. Electron density have no idea about that. So if all of our electrons are just stay and does not move, or if our 3 electrons move quite quickly, think about these two different cases. However, if we just describe the number of electrons at a given position, then we will say, oh, there are 3 electrons in a box. So the density will be 3 divided by the area or volume of this box. That will be our answer. You know that these two cases will show quite much different behavior because this one does not contribute anything to our current density, and this one can or may contribute to the current density significantly. So they are quite different, but when we consider only electron density, they look similar and no differences in terms of electron density. So simply speaking, we need more information. We need the information about velocity. How fast are they? Are they just staying there, or quickly moving toward a certain position? That is an important question. However, point is BT, Boltzmann transport equation, can give us full information about velocity distribution. So it can have many information because it has full knowledge about position and momentum space distribution. However, sometimes that is too much. So sometimes that is just overkill for our purpose. What we want to do eventually is just to calculate the electron current density, because electron current density is used to calculate the terminal current, and this calculation of terminal current is of our most concern. So sometimes we feel that, oh, distribution function itself is not required for our simulation purpose. We just wanted to know electron density, of course, and current density. So if we restrict ourselves to these two physical quantities, how many are they there? How many electrons are there? And how fast are they? If we restrict in this sense, then maybe we can develop a much simpler model than the Boltzmann transport equation. That is our idea. However, since as you can see that the Boltzmann equation really well describe the motion of our electron system, so if our simplified equation is in contradiction to the Boltzmann transport equation, then it will be wrong. Therefore, we have to develop a simplified equation for these quantities, which is consistent with Boltzmann transport equation. So how can we develop such a simplified equation, however consistent with BT? One way suggested in this lecture course is just to consistently derive this simplified equation directly from BTE. Starting from the Boltzmann transport equation, we just made certain projection of Boltzmann transport equation into the subspace, so that will give us a simplified equation. Okay, so how about our strategy? It means that more specifically, Boltzmann transport equation is defined on real space and momentum space, phase space, but our goal is just to say we wanted to have electron density and current density only as functions of position. So this velocity information or momentum information is not required. Instead of that, previously we had only one single unified expression, so distribution function, but instead of that we introduced two different quantities. Oh, all kinds of complicated behavior or description about entire momentum space can be just merge it into just number 2. The entire space, three-dimensional K-space, momentum space, is just described by just number 2. That is our great simplification. So originally Boltzmann transport equation is, for example, 6-dimensional problem due to the 3-dimensional Fourier space and due to 3-dimensional momentum space. But after this simplification, we can have just a 3D problem. Oh, 3D problem is readily accessible to us with our high-performance computing machines. So this becomes really accessible to us. Okay, so our aim is now how can we smartly eliminate this dependence. So here we have a momentum dependence, but how can we make some clever way to eliminate it without losing much information? That is the point. Okay, so let's go to our lecture contents. So our eventual goal is to derive drift diffusion equation. So here DD is drift diffusion equation. It simply means that we have to derive two equations for each carriers. For example, for electrons, we have to include or we have to derive two equations for electrons. And also for holes, we have to introduce or derive two equations. So two equations and two equations, and of course we have Poisson equation. Oh yes, we have a Poisson equation here. So in usual sense, when you say drift diffusion equation, we just treat these 5 equations as a whole. I mean that 5 equations, set of 5 equations is called drift diffusion scheme. So we have to solve 5 equations at the same time. However, we have good knowledge on the Poisson equation already, and structurally these electron equations and hole equations are quite similar, almost identical. So in this course, I will just show you the derivation for electrons. Derivation for holes follows the exactly same procedure, so I will not repeat it again. Remark is, although we will derive only 2 equations, however, that just makes a set of 5 equations. So we will try to derive so-called continuity equation and another equation for current density, and these are for electrons. However, just copy and paste, we can generate also whole continuity equation and whole current density expression. And since we have Gauss law or Poisson equation previously, we can easily construct a set of 5 equations. Yes, so we have continuity equation and the equation or expression for the current density. So the continuity equation is for the electron density, and this current density expression is for electron current density. So we will derive 2 equations for them. Okay, then let's go to the first case. The first case is continuity equation. We will try to derive the equation called continuity equation. Of course, continuity equation can be applied to many different quantities, physical quantities. So in this case, we have to specify that we are now talking about electron continuity equation. Because we are now talking about electrons, and if we are doing it for holes, then we will have a hole continuity equation. So please think about the definition of electron density. Electron density, in a rough sense, we can define it. Think about certain volume, small volume, and think about the total number of electrons inside this small volume. So say we have calculated number n, and say this is the volume is V, then n over V equal to the electron density. That will be the simple definition for our electron density. Then think about this one. Then how can we calculate this n and V? Think about this. Say we have, for example, Lx and Ly and Lz. Then how can you calculate the total number of electrons inside it? So then we have to make a summation about triple summation about quantum numbers, quantum number I, J, and K, and we have to, for example, have D. Yes, that is required, because this triple summation just count the number of available states, and each state have its own occupancy. So if occupancy, the distribution function, is close to 1, then this state is almost fully occupied, and it contributes to the total number n. And if that is 0, so if this one is 0, although there exists a state, but it is just empty, and it does not contribute to the total number of electrons. That was the simple number counting problem. However, we have studied that we can easily convert it into just integration and integration and integration over our k-space dkx, dky, and dkg. Of course, this integration introduces additional dimension. So therefore, in order to make it just a number, we have to consider Lx, Ly, Lz, and here we have 2 pi, it's a cube. And this triple summation can be just casted into triple integral. And here we have the quantity distribution function, and now we have quantity distribution function. And maybe you remember that this Lx, Ly, Lz can be treated as volume of our box. So n over V, which is defined as electron density now, can be expressed as 1 over cube of 2 pi and triple integral dkx, dky, dkz, and distribution function. That is the thing we have covered in our previous lecture. So when you consider the box problem, three-dimensional box problem, we have already introduced this expression. Okay, and here you can see that this is exactly corresponding to our expression shown here. You know that electron density is given by 1 over cube of 2 pi and triple integral. So here I have introduced a little strange notation, dk although that is written in this way, please regard it as just a triple integral. So this is not a vector at all. The more, or how can I say, more reasonable way would be, for example, D3K. Maybe that would be more frequently adopted way to represent it, but please, anyhow, think that this integral dk is just a shorthanded form for this notation. Okay, so now you understand our electron density can be expressed as this form, just integration of the distribution function over our momentum space. So that gives the information. So let's say if you wanted to calculate the electron density, then what you have to do is just to integrate the distribution function over momentum space. Then let's say if you are interested with the time variation of your electron density, then what you have to do is just you have to calculate the integration of your distribution function over entire K space, and this is corresponding to your n, and taking the time derivative. That will be the right operation to be performed. And you know that here we have integration over momentum space, integration over momentum space, and derivation with respect to time, and they are independent variables, and their order can be switched. So we can say 1 over 3 and round f or round t integrated over momentum space. That can be an expression for round n over round t. So simply speaking, if we integrate our round f over round t, time derivative of our electron distribution function over the momentum space, that will give you round n over round t. Wow! So please remember that we are mostly interested with electron density, and we wanted to know the time variation of electron density. It simply means that if you really wanted to know round n over round t, then you have to integrate round f over round t. That is main message. So Boltzmann transport equation already describes round f over round t. So by just performing the momentum space integration, you can get round n over round t. That is the main idea. Okay, so now we just perform the integration of Boltzmann equation over the momentum space. That is written here. So please have a look at this equation. You can see that here we have round f over round t, and here you can have velocity times gradient of phi with respect to real space, and 1 over half force times gradient of f with respect to k, and here we have scattering. These are just terms in the Boltzmann transport equation. And what we have done in this slide is just performing integration, and also integration and integration. You can easily understand there is no new information, and it is just integrated Boltzmann equation. But since we have performed the integration, the resultant equation is no longer defined on 6-dimensional phase space, but it is now defined on 3-dimensional real space. Already by performing this integration, we reduce our dimensionality drastically. Okay? The first term can be easily recognized as round n over round t. So we have discussed it already. So now we can say the first term is written as round n over round t. So we have remaining 3 terms, and just copied and pasted in my next slide. So please have a look at it. So here and there, they are just copy and copy. Okay, here, and you can see that the right hand side term, this is related with the scattering, and this term is just vanishing here. So please think about this one. The right hand side, we have to perform the scattering over the momentum space. But since we are assuming a local scattering, so scattering can abruptly or instantaneously change the velocity. However, it does not change its position. The electron position is just kept as before, and only velocity changes abruptly. So although in a phase space, the motion of our electrons just looks like this. So previously it was there, and after that, after scattering mechanisms, scattering events, it goes to suddenly. So this is a time equal to 0, and this is just 0.3 picosecond, and also 0.3 picosecond scattering events occurs, and it goes to here. And even in this case, if we integrate our scattering over momentum space, in this case velocity axis, then we will have just 0 value, because we will say that for this position, oh, one electron moves away, so we will have -1. And however, at a new destination, we will have net incoming electrons, so we will have just a count of 1. So this -1 and +1 are just exactly balanced. Otherwise, if that is not exactly balanced, then what will happen? We just describe the generation of electrons or annihilation of electrons. That never occurs in our description. So we have to say these numbers are perfectly balanced. So when we integrate our scattering over momentum space, that gives us exactly 0, because number of electrons inside a given position should be preserved. Okay, so now we can say the terms related with scattering on the right hand side should be 0. Okay, here we have 0 here. Up to now we haven't made any approximation, but in this step we have to introduce an approximation. The approximation is now band structure is position independent. That is assumed. I mean that in general, our velocity here, group velocity can be a function of real space and k space. However, in this position independent band structure, we assume that velocity is just a function of momentum. Think about a silicon device where everywhere we have just silicon. Then if we change the real space, the band structure will be the same. So when the momentum is just given, then velocity will be the same. So we can easily agree with this approximation. By introducing the position independent band structure, one thing we can have is like this. The integrand in the second term is given by this one. However, in general case, V can be a function of R and K. Also, distribution function can be function of R and K. In this case, we cannot pull out this distribution function. For example, this is not allowed. F V. It is not allowed. Why? Because even our velocity can have dependence on the velocity, position. So then what we have to do in order to have equality here is just minus F times this additional term is required to have the equality. Okay, this is just nothing but vector identity. So we have this form, but fortunately, by adopting the position independent band structure, and now our real space divergence of velocity here, since it is not related with the real space, so this term can be neglected. Oh, so in this position independent band structure case, now this integrand can be simply written as real space divergence of F times V vector. Okay, then this real space divergence is nothing related with this momentum space integration, so it can pull out here, and now we can just perform the integration of a quantity velocity multiplied by distribution function. That is one thing. So from this equation to this equation, we have to introduce position-independent band structure. That is one thing. And we have another thing to be covered in this lecture. It is the third term in the left-hand side. So in the third term, here we have force and gradient of F with respect to K. And force in this course simply given as the electric force. So we have just minus Q times electric field. And you know that electric field is just a function of a position, not related with the momentum. Of course, if we are talking about the Lorentz force, then Lorentz force really depends on the momentum. So life will be much more complicated, but for a while we will just consider the electric force. So now this force itself is also only a function of real space. Then we can easily pull it out here. Okay. Now we can pull it out here. Then remaining thing is just integration of gradient of K with respect to our momentum variable. Okay, so you know that here this is nothing but taking derivative and integrating with respect to same variable. So what will happen if you have a similar thing? You have F and d over dx and integration from A to B. What is your result for this operation? You will have just F evaluated at B minus F evaluated at A. The boundary values of your integral boundary of your integral range is required. Quite similarly, although this is not one-dimensional integration but three-dimensional triple integration, but you can easily understand by performing this integration, you need to the values at zone boundary. So distribution function at when your K value is quite large. Then your assumption is your electron distribution has the highest value where energy is quite low. And if we go to the end of our K space, then the distribution function also vanishes. So this is also an assumption. However, I think that this is really reasonable. So think about your K space and your all electrons are densely populated around the origin of your K space. And if you go to this or to that direction, your K value increase and your energy value also increase, and therefore these points, these boundary points are all corresponding to extremely high energy positions. And for these states with extremely high energies, then they are not usually occupied by our electrons. So we can say by performing this integration, this red colored integration gives you just number 0. So the entire third term can be regarded as just 0. So now we understand originally Boltzmann equation have 4 different terms. One is related with the time derivative, one is related with the velocity, and third term is related with electric force, and the right hand side we have scattering term. However, by taking the integration over momentum space, third term and fourth term vanishes, and only we have two terms remaining. Okay, so let me conclude my talk today. So now we have only two terms, and the first term is easily recognized as round n over round t. And now we have the terms like this: divergence over certain term, and this certain term is just given by integration of velocity times distribution. So velocity times distribution. Velocity means that how fast is it, and distribution is how many are there. So by combining these two information, we can construct the quantity corresponding flux. So how many electrons and how fast are they? So we can introduce a new quantity called electron flux F sub n. Don't be confused with the electric force F itself. Here we have a subscript n to show that this is flux, not force. And electron flux is simply defined as just multiplying velocity to our distribution function and taking the momentum space integral. Then we will have this form of continuity equation. So simply speaking, this quantity is identified as F sub n. So now we have this continuity equation. Okay, time is up, so I will stop here, and we have a discussion not covered in today's lecture. We will continue it in the next lecture, and next Monday, and there we will try to derive an expression for electron current density J sub n. Thank you for your attention, and see you Monday. Bye.